Damn it. Okay, I'm starting to record now. So a sequence is a set of vertices. So A1, comma, A2, comma, A3, comma, dot, 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 right? I guess more formally, you can see it as a function. Like A from the natural numbers, right, to some domain, right? So this some domain. And this domain is sort of where the A sub I live in, right? So, so for now, we're going to take D equals the real numbers, right? So we're going to only consider real valued sequences, okay? And so in the real numbers, right, we have an ordering. We can say when A is less than B, right? A is greater than B, A equals B, right? And so we can say a sequence is increasing, A1, A2, dot, dot, dot is increasing if A1 is less than A2, is less than A3, is less than dot, 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 right? And it's decreasing and non-increasing and non-decreasing. Hopefully those definitions are also clear. Okay. So there's a very nice theorem. Maybe I shouldn't call it a theorem. It's called the lemma, right? And we call this the peak point lemma. Based on the argument that is used in the proof. So the idea is that any sequence, any real valued sequence, so that just means sequences where the elements are real numbers, has an increasing subsequence, and I should define subsequence. Or a decreasing subsequence. Let me move this. Or a decreasing subsequence. Okay, and what do I mean by a subsequence? So a subsequence is just a subset. So AI1, AI2, dot, 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 right? Where I1 is less than I2, it's less than I3, it's less than dot, dot, dot. So, you know, for example, we can have like the subsequence A2, comma, A4, A6 of even valued indices. So there's a question in the chat. Isn't this false? So, oh, I see. Yes, this is false. So what I meant to say is non-increasing subsequence or a non-decreasing subsequence. And these things aren't mutually exclusive, right? Constant sequences fall into both. So yeah, that's a good point. All right, so let's prove this theorem. As a reminder, we have, so the theorem says that given any real valued sequence, we can take a subsequence that is either non-increasing or non-decreasing, which is really amazing, right? Just given right the ordering on the real numbers, we can say something very general about any real valued sequence and whether or not it has non-increasing or non-decreasing subsequences in it. So the proof goes something like this. Okay, so we're going to define something called a peak point. So a peak point, A sub j, right? We call A sub j a peak point. So if it has the property that A sub j is greater than or equal to A sub k for all k greater than or equal to j. Okay, and so what this means is that, well, if our sequence, right, we can sort of graph our sequence. So if this is A sub j, right, then all the A sub k's, right, for k after j, right, so this should be j and this should be k, are going to be below like this line. Okay, so a peak point a sub j is just a point that's greater than greater than or equal to all the terms after it, right? Okay, so there are two cases. Okay, there are two cases to consider. Okay, the first case is when there are infinitely many peak points. Okay. All right, and so when there are infinitely many peak points, right, there's a subsequence of them, right, because we can put them in order. Then there is a subsequence, a sub I1, comma, a sub I2, comma, a sub I3, comma, dot, dot, dot of peak points. All right. And so here's where I get to ask you all a question. So let me pull it up. Okay, so I'm going to launch the poll, right? So the question is, right, so now I found a subsequence of peak points right here, right? So now, what is this subsequence? Is it non-increasing, non-decreasing, neither, or other? And so I'll give you guys some time to answer. So I've given you a minute to think about that, right? So for the recording people who are watching this after the fact, so here's the question, right? So I found a subsequence of peak points, a sub I sub 1, a sub I sub 2, a sub I sub 3, dot, dot, dot. Then the subsequence is what? So the correct answer is that the subsequence is non-increasing, okay? And the reason why this is because, so this subsequence is entirely of peak points, right? So a sub I sub 1, right, is a peak point, right? And so like I sub 2 and I sub 3 and dot, dot, dot are all going to be greater than I sub 1, right? So since it's a peak point, right, a sub I sub 1 has the property that it's greater than all these for all k greater than or j. So, right, so a sub I sub 1 is greater than all of these, and by similar reasoning, a sub I sub 2 is greater than or equal to, excuse me, all of the what is the opposite of preceding? All the terms after it. So we have, so the answer is, it's non-decreasing. Decreasing or increasing? It is non-increasing, that's right. The answer is it's non-increasing, right? Okay, and here's the second case, right? So the second case, right? So the first case is there are infinitely many peak points. The second case is there are only finitely many peak points. Okay. And for this, I'm going to launch another poll. And this one has two questions. So you might need some time to think about this, right? So first, given your finitely many peak points, a sub j sub 1 through a sub j sub n, you want to choose a sub I sub 1, right? You want to choose your subsequence such that I sub 1 is blank. And after we choose a sub I sub 1, how should we choose a sub I sub 2, right? So I'll let you guys think about that for a minute or two. Recording. Okay, so, all right, so let's discuss this, right? So we have finitely many peak points, right? A sub j sub 1 through a sub j sub n, dot, 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 well, dot, 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 right? So how should we want to choose our a sub I sub 1? Well, the idea is that we should choose a sub I sub 1 that is not a peak point. Okay, Right. And so basically we want to choose, well, so so this item and this item are both right. So once we choose a sub I sub 1, right? So a sub I sub 1 is not a peak point. Okay? And so we want to choose a subsequence, right? So this subsequence is, oh, my pen spazzed out. So the subsequence we found when there are infinitely many peak points is non-increasing, right? So now we might want to find a, so now in this case, there might be a sequence that is non-decreasing. So a sub I sub 1 is not a peak point, and so by definition, there exists some k greater than I sub 1 such that a sub I sub 1 is less than a sub k, right? And we're going to let k equals I sub 2, right? So I sub 2 is greater than I sub 1, and a sub I sub 1 is less than a sub I sub 2, right? So this, right, well, I guess you need to be careful. So I sub 2, right? So if you chose that a sub I sub 1 is greater than all of the jk, right, then you can say that, oh, I see. Maybe, yeah. You have to be careful when you're choosing this, I guess. But if so, let's go with this option. So I sub 2, right? So I sub 1 is greater than any of the jk. So I sub 2 is also greater than any of the jk, right? The j sub k, right? So it is also not a peak point. So a sub I sub 2 is not a peak point. Am I still recording? Yes. And so we can find I sub 3, right, such that I sub 1 less than I sub 2 less than I sub 3, and a sub I sub 1 less than a sub I sub 2 less than a sub I sub 3, right? Okay, and then in this way we get a non-decreasing subsequence, or more specifically, we get an increasing subsequence. So we get an increasing subsequence. So if we go on forever or recursively, or we get an increasing subsequence in this case. Okay. All right. So that is the proof that we worked out together of the peak point lemma, right? And so this is actually a special case of what's known as the infinite Ramsey theorem. And so we're going to motivate the statement, and then we're going to prove the statement. So what we're going to do, right? So first, I'm going to introduce what a graph is. So so a graph, right, is a set, well, a pair of v comma e, where v is a set of vertices and e is a set of edges. Okay, which is a subset of v cross v. Well, it's not exactly, which is edges, which are pairs of vertices, which are sets of two vertices. Okay, and so let's take this graph, right? So just so we're used to this definition, it has two vertices, right? So the vertices set is 1, 2, and the edge set, there's one edge that connects 1 and 2. So the edge set looks like this, 1, 2. Okay, and so a complete graph All right, so E is a relation on V. That's a good way of thinking about it too. So a complete graph is one where every vertex is connected to every other vertex. Okay, so let's say we have a complete graph on 3 vertices would look like this, right? So we connect every vertex to every other vertex. On 4 vertices, it would look something like this, right? So we connect this vertex to this one and this one to this one, and we have 6 connections. And with 5 vertices, it looks something like this, and so on, right? Like that, right? So this is in the finite case, right? So I'm going to soon talk about the infinite complete graph on the natural numbers. Okay, so a complete graph is where every vertex is connected to every other vertex. So the infinite complete graph on the natural numbers, right, is, so we'll denote it as G equals, so the vertex set is the natural numbers, and the edge set is, I'm going to write like this natural numbers choose 2, which I'll make precise right now. So the vertex set is the natural numbers, right, and the edge set, right, is A comma B, where A and B are in the natural numbers, and the size of A comma B is 2. So we could put this here. So it's where every vertex is connected to every other vertex, right? So you could think about it like this. And then 4, and then we'll have to connect 4 to all the other 3. And then we continue with 5, and it gets to be a big mess, right? Okay, so now that we have this infinite complete graph on the natural numbers, there are some questions we can ask about it. And so what we're going to ask about is colorings, right? So given this graph, we can color it, right? So either its vertices or edges. Okay, let's consider what happens if we color its vertices, right? So if we can, and for the sake of this talk, right, so vertices can be colored either red or blue. Vertices / edges. So they can be colored either red or blue. Okay. So let's consider what happens if we color the vertices, right? So we can assign each natural number a color, right? And so it would look like we color this red, and this one will be blue, and this one will be red, and so on, right? And so the point to take away from this is that there will either be infinitely many vertices that are red or infinitely many vertices that are blue, right? And this follows from the pigeonhole principle. So now let's consider what happens if we color the edges, right? And so this is Ramsey's theorem. So Ramsey's theorem. On n choose 2. So this is what we're going to prove. And okay, I have an hour left, which is pretty good. No, I'm at 30 minutes left. Yes, I can't do calculations in my head. So we have Ramsey's theorem on this. Okay, so given any coloring on the edges, okay, of the infinite complete graph, So we're going to color the edges red or blue, right? So the statement is that there exists an infinite subset of vertices oops, my pen's passed out again. Okay. So a sub 1, a sub 2, dot, 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 right? Whose edges, right, between them are either all red or all blue. Okay, so that given any coloring on the edges of the graph, which I may or may not have erased already, on the edges of the infinite complete graph, then there's an infinite subset of vertices, right? So that we choose them, and then the edges between all of them are all red or all blue. So it would look something like this. It would look something like that. All right, and let me show you how to prove something like this. Okay, so the edges, right, have the form, you know, so the edges have the form, you know, I comma j, right? So so I wrote them in pair form, but I can distinguish their order, right? So the edges have the form I comma j where I is less than j, right? So let's okay, and let's define v1 equals 1. All right. So now, okay, and let's denote the color of I comma j to be, let's just say color of I comma j. So COL for color. So let's define v1 as being 1, right? Okay, so here's what we're going to do. So we're going to consider this set. Okay, we're going to consider 1j, 1 comma j, right? So j is in the natural numbers, j is greater than 1. So all the edges that are connected to 1, right? And then color, actually, so we're going to consider this, right? And then we can divide it into two parts, right? The part whose edges are colored red and the part whose edges are colored blue. So we're going to consider this set S1. We're going to call it S1, right? So, and then we're going to let R be, so R is going to be, okay. So let R in S, right, be, so the 1j in S, right, such that the colors of 1 comma j is red, right? And let B, right, be the subset of S such that, excuse the terrible notation, 1j is in S such that, you know, the color of 1 comma j is blue, right? And since every edge, right, which is connected to 1 is either red or blue, right? So R union B is S1, right? So R union B is S1, right? So by our observations earlier, right, so there are infinitely many vertices, right, connected to 1, and they're either colored red or blue. And so the observation is that one of these two sets is infinite. Okay. And so we'll take, let's say it's just the red. So let's just say it's R, right? Okay. Now we're gonna rename R. S2. We're going to rename R to S2. Okay? And so, all right. And so now, so we've done this process, right? So we picked a vertex V1, which happens to be 1. We've considered all the vertices which are connected to 1, right? They're either colored red or blue, and we picked the infinite subset of all that. Okay, so one of these two sets is infinite. Okay, so denote its color, right? Ooh, my board space use is not very good, but it's okay. By C1. Okay, so we have a set S1, right, which is all the vertices connected to 1 or V1. We defined S2, right, which is an infinite subset of S1. And we have the color of all the vertices connected to 1 are one color, which we'll call C1, right? So now we have S2. Okay, so now we have an infinite set, S2. Okay, and so now we're going to choose some vertex V2 in S2. Okay, and then we're going to do the exact same thing as we did up here, right? So, let R equal, so V2. Well, let's choose V2 to be the least element of S2, which, exists by WOP, right? So V2J, right, such that in S2, right? So V2J is so J is in S2, and the color of V2J is red, right? Is red. And we can let B equal the same thing. So the same thing, the color of this is blue. Okay, so we can do the exact same thing, right? And one of these sets will be infinite, right? By the exact same reasoning that we did on V1 and S1. By the same reasoning. Okay, so we'll call this set S3. Okay, so hopefully everyone sees where I'm going. I'm going to go forever with this and then keep going. So, and then we're going to call the color C2. Okay, so keep going. Okay, and so, all right, so we get 3 sequences, right? So we get S1, right? S2, S3, ... We get a sequence of vertices, V1, V2, let's write N here, V3, ... And we get a sequence of colors, C1, C2, C3, ... right? And now I'm going to launch a poll about coloring. So, oh, no, that's the wrong poll. Right. So, all right. So the poll asks you so which of the SN is, so VN is in which of the SN? So I'll let you work on that for a minute or two. All right. So let's see. So it looks like most people said that. So VN is in SJ. for 1 less than or equal to j less than or equal to n, right? So I think this is the correct one, right? So let's consider, right? So v1 was in n, right? And S1, right? So we have this containment, right? Because we chose S1 and S2 and S3, right, to be strict infinite subsets of the previous. So we have this set containment, right? And so V2, right? So V2 is defined as something in S1, right? So V2 is in S1. Oh, I think my poll is faulty. I think this should be strict less than or equal, but I didn't address, I guess I didn't address whether V2 was in S2 or not, but we have this containment V3 and S2, V4 and S3 and so on. So what it should be is that, V3 should be in these two subsets and not any of the subsets after. So yeah, so the idea is now we have a set of subsets, a set of vertices, and a set of colors, right? And so the colors, right, mean that, so C2 has the property that every vertex in S3, right, connected with V2, they all have the color C2. Maybe it was S2. It's okay. So we have, let me mute. Okay, great. Problem solved itself. So, all right, so let's finish the proof, right? So we have a sequence of vertices. V1, V2, V3, ... right? And colors, right? C1, C2, C3. And so what happens, right, is that, so what we're going to do is, since C1, the Ci are either red or blue, right? So red or blue. And so what happens is that, let me meet that guy. Okay. So what happens is that there's going to be an infinite subset that's all the same color, right? So choose, oops, I want it to be black. Okay, choose V sub I sub 1 ... V sub I sub 2. So an infinite subset, just like we want, such that C sub I sub 1 equals C sub I sub 2 equals ... right? And so now this is the subset we want, right? Because, so the reasoning is that, so let's consider V sub I sub 1, right? So V sub I sub 2, right, is going to be contained in V sub I sub S sub I 1. Either it's S sub I1 or S sub I1 plus 1. I can't recall the exact details, but the idea is that V sub I sub 1 is connected to V sub I sub 2 in a way such that the way we chose this, right, was that all the things connected to V sub I sub 1 are all C sub I sub 1, right? And the colors that are connected to V sub I sub 2 of all the things after that are C sub I sub 2, but they're all equal. So we get our so-called so we get our subset of vertices whose edges connecting them are all the same color. Okay. All right, so that was the proof, right? So let me clear this and then my board will lag a lot less. So let me talk about the corollary. Okay, so the corollary is that theorem. So yeah, so any real valued sequence has a non-increasing or non-decreasing subsequence. Okay, so let me talk about this corollary, right? So let me show you how this fact, right, which we proved in the beginning, follows from the theorem we just proved now. So the proof is that we color n by the following rule, okay? So we're gonna color it by red if a sub I is greater than or equal to a sub j, right? Where I is less than j. And then blue if a sub I is less than or equal to a sub j, if I is less than j. And if they're equal, it doesn't matter. You can color them whatever you want, but the theorem we proved tells us there is a subset of vertices. So let's say I1, I2, I3, dot, 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 whose edges between them are all red or all blue. So let's think about what happens if the edges between them are all red, right? So what that means, right? So I1 has a red edge with I2. That means that a sub I sub 1 is, well, so let's say that that means that a sub I sub 1 is greater than or equal to a sub I sub 2, right? So a sub I sub 1 is greater than or equal to a sub I sub 2, right? Oh, I'm cutting out. That's not great. But so, okay, let me just repeat what I said then. Okay, let me just repeat. So what it means, so let's just say that these vertices are all in order, right? I sub 1 is less than I sub 2, is less than I sub 3, right? So a red edge between I sub 1 and I sub 2 means that a sub I sub 1 is greater than or equal to a sub I sub 2, right? And then we can do the same thing, right? The red edge between I sub 2 and I sub 3 means that a sub I sub 2 is greater than or equal to a sub I sub 3. And then we can keep going. So we get an increasing subsequence, non-increasing subsequence. Okay. So that's this thing, right, is a corollary of the theorem we just proved. Let me note that, so the way we proved this theorem originally, it's not strong enough to show the theorem. So we proved that theorem in essentially a different way, but this is sort of the overpowered way of showing that any sequence has either non-increasing or non-decreasing subsequence. And so I have a little bit of time left, less than I would have hoped, but maybe I can talk about how things go when everything's finite. Since so far I've only talked about infinite things. So the finite case. Okay. So let me just quickly discuss the finite case, right? So in the finite case, we have a complete graph, k to the n, right? So a complete graph, right, of course, is where each vertex is connected to each other vertex. And we'd like to ask whether or not a complete graph contains, so either a red K, let's say K sub M, or a blue K sub M. So what do I mean by this? So let's draw out an example with 5 vertices. So if I draw this example with 5 vertices, right? So, and I connect these 3, and maybe I'll connect these 2 with blue, and then these 3 with red. So you'll notice that there's a red triangle, right? And this is what I mean. So this graph contains a red K3, right? So the vertices, right, with the edges between them, right, are all red. And so we'd like to, so given a complete graph Kn, we'd like to ask whether or not a complete graph contains either a red Km or a blue Kn, right? So the, I guess the nicest result, and the one that I guess many of you probably have seen before, is that we can formulate it like so, right? In a group with 6 friends, okay, there are either 3 complete strangers or 3 mutual friends. Okay, so actually, so to show this, it's better to show a picture. So let me search it up. Ramsey theory. Let me search up a picture for, yeah, this will do. Okay, so to demonstrate this theorem and why it's true, let me show this theorem. So here's a group of 6 mutual connections, right? Oh, they're missing an edge in between them. Let's draw it like this. Okay. Yeah, okay, so this is like 6 friends, 1, 2, 3, 4, 5, 6, right? And we want to show that 3 of them, and let's say that red is friends and blue is not friends. Okay, and so we want to show that either three people are friends with each other, which seems to be the case here, or 3 people do not have any friend, or 3 people, among 3 people, none of them know each other, right? So the argument sort of goes like this, right? So fix any vertex, right? So we're gonna look at vertex number 4, right? And we're gonna look at all the edges, right, between every other vertex and 4. So that would be this one, this one, this one, this one, and this one, right? And these have the colors, you know, red, blue, blue, red, and blue. Okay. And since there are 5 different connections, right, and 2 different colors, it must be that 3 of them have the same color when connected with 4. So 4 has at least 3 non-friends or 3 friends, right? So here are the 3 non-friends. Okay, so 4 with 6, 4 with 1, and 4 with 3, right? So now let's consider the edges between 1, 6, and 3, right? So either, right, so either 1, 6, and 3 will have a blue edge in between them, right? In which case, so if like 1, 6 was blue, right? Let's pretend 1, 6 was blue for a second. Then 4 to 6 and 4 to 1 and 1 to 6 would be the blue triangle we want, right? but it doesn't turn out that way, right? It turns out that none of these are blue, but then they're all red, right? Which means we have a red triangle like this. So that's sort of how the argument goes, right? And so I'm out of time, but what I'll mention is that we can generalize the argument above to show the following. So given, so given m, right, in the natural numbers, is there n greater than m such that any red-blue coloring, so in any red-blue coloring of the complete graph on n vertices, there is a red km or a blue km? And the answer is yes. Okay. And one proof, right, would use similar reasoning to maybe this argument. Well, anyways, I'm out of time. So hope you enjoyed my talk. I know I'm terrible at talking, but hopefully it managed fine. Yeah. So any questions, just feel free to ask them. And yeah. Oh, I can stop my